Hey, welcome back. So let's have a look at atomic solids or atomic crystals. And we sort of divide these up into three different categories. So depending on how the atoms are joined together. So if they're just non-bonding, so there's no covalent or ionic bonds between them, you've only got essentially London dispersion forces. So that's pretty wimpily held together. And they are going to have very low melting points, very low boiling points, right? These kind of things. So what are we looking at here? We're looking at things like xenon. So xenon crystalline has a melting point of minus 110 degrees C. It's kind of large, really, because xenon's a very large atom, a lot of electrons. So it's going to have quite a few London dispersion forces, but still pretty low melting point. Something like helium, of course, you've only got a couple of electrons, so you've only got a very minute London dispersion force. So you're looking at 1 degree above absolute zero, so 1 Kelvin or minus 272 degrees Celsius. Pretty wimpy stuff. Now, if we go to the other couple of categories, we've got metallic crystals, and so metallic crystals are held by metallic bonds, and we first looked at these in the first semester, I believe, and you essentially got an electron C around a positive kernel. So for instance, if you got something like sodium, our way of thinking of sodium is that it's actually composed of these kernels of essentially sodium ions, and that valence electron is essentially just kind of spread out over and around and the rest of the ions here. So they're delocalized, that is to say the electron isn't exactly surrounding the atom or the ion it originally came from, but instead you've got this sea of electrons, so it kind of spreads out everywhere. And of course you can polish these and turn these into mirrors. This electron sea is what reflects the light back at you when you look at yourself in a mirror. Something like sodium's going to have a melting point of about 100 degrees C, which is not bad at all actually for a melting point. Whereas if you go to something like magnesium or aluminum, you're going to see a much larger melting point. So magnesium's about 650 degrees C, and aluminum's about 660 degrees C. And certainly the strength of this metallic bond seems to be proportional to the number of valence electrons. So the more electrons you have in the electron C, the more tightly held these kernels are together, and so the harder it is to melt these crystals. The last kind of atomic crystals are ones where you've got a covalent bond holding the atoms together, but we call this actually a network covalent crystal because those covalent bonds are spread out throughout the entire structure itself. And because covalent bonds are exceptionally strong, these crystals are exceptionally strong and extremely high melting points. So let's go ahead and turn the slide over and look at some network covalent crystals. So this is graphite, you might remember from an earlier video. And so graphite's one of those things that's only found in a few places in the world. And so it used to be quite expensive because of that. And the graphite is made up of these carbon atoms in these hexagonal sheets that kind of lay one over top the other. And they're like sheets of paper in the sense that each sheet is actually kind of strong. But if you have the sheets, right, in a big pile, they fall, one layer will kind of slip over the other quite easily. So as you go ahead and you write on a sheet of paper, right, you can kind of break these sheets away from each other and leave them behind on the paper itself. Another example of a covalent crystal, by the way, is diamond. And diamond consists of this tetrahedral arrangement. So if you look at each atom there, you've got that tetrahedral arrangement of atoms. It's kind of hard to draw, actually, so I'm definitely not an expert here. But each atom has that tetrahedral, so it's sp3 hybridized, right, that 109.5 degree bond angle, and extends throughout the entire crystal. Whereas when we look at something like graphite, graphite has that sp2, that trigonal planar, that 120 degree kind of arrangement. And you might say, well, what about that extra electron? Well, that extra electron, remember, is an unhybridized p orbital. And so you've got these sheets that have these unhybridized p orbitals with a single electron, and this electron is highly delocalized over the whole sheet. So graphite is extremely electrical conducting because those electrons can be kind of pumped in and pushed out from one side to the other. Remember, those individual sheets we call graphene, whereas something like diamond is not so conductive at all. In fact, for most intents and purposes, diamond is considered a non-conductor of electricity. It doesn't have that free valence electron to play with. Just to give you an example of how strong the bonds are here, we've got a melting point that is exceptionally high. So somewhere on the order of about 3,800 degrees Celsius. So if you're going to make a window in space that can, sort of approach the sun and not melt, diamond's a very good material for it. So it's essentially a giant molecule. So if someone gives you a diamond ring, the whole diamond in the ring itself is an entirely large macromolecule, right? It's so large you can actually see this molecule with your eye.